This section, we're kind of taking a break from factoring and just doing a refresher on radicals, how to simplify radicals, how to rationalize denominators. You should have done radicals or worked through radicals in Algebra 1, so this should be a review, I'm hoping, for everybody. But it's important you have a really good grasp of how to simplify radicals as we move on into the quadratic chapter, because you're going to find some of your solutions are going to have radicals in them, and you need to be able to work with them. We do have a quiz tomorrow over 5.1 through 5.4, including this section. So once we finish going through this in class, make sure you're trying to do as many problems as you can in 5.4 to get help, or come in before school tomorrow to get ready for that quiz. Okay. So first question, the number under the radical sign is called the what? Radicand. Radicand. So if I talk about the radicand, you'll know I'm referring to just the number under the radical sign. And the radical sign is the square root sign, or the root sign, I should say. It's not always a square root. It could be a cube root. If it's a root like this with no number inside, you always know that number is a 2. Just like when you write x, you don't have to put a 1 in front of it because you know the 1's already there. It's just implied. It's the same with the root. If it's a square root, it will not have a number inside right here. If it's a cube root, you'll have a 3 there, 4th root of 4. But if it's blank, that means there's a 2 there. It's a square root. Okay, so if you're adding roots, can I add these two? I can't. And I'm going to go through a few rules with radicals, but you cannot add roots that are unlike. This number is, well, square root of 4 is 2, right? Square root of 10, let me just do that. Square root of 6, I should say, is 2.44. I'm going to do this. 3 square roots of 4 plus 2 square roots of 6. So 3 times 2 is 6. 2 times the square root of 6. The square root of 6 is about 2.45. If I multiply that by 2, I get 4.9. So this is equal to about 10.9, approximately. Okay. If I were to add these two together to get 5 square roots of 10, 5 times the square root of 10 is 15.8. Okay, so you can't add radicands, if you will, inside the root. You can't just add across. It doesn't work. So this one is false. Okay, question 3, is the square root of 3 times the square root of 5 the square root of 15? This is true. You can multiply radicands to get one simplified radical. Okay, but you can't add them. Question 4, to simplify a radical, you should look for factors of that radicand that are what? Square roots. Square roots. So if we have the square root of 50, this is not simplified. The reason it's not simplified is there is a factor of 50 that is a perfect square. What are perfect squares again? Give me some examples. 16, 4, 25. So if I were to just have kind of the perfect squares, right? Those are the first 9, right? And when you're simplifying radicals, writing them out like this might be helpful to you, just on the side of your paper as you're simplifying them. Pretty soon you'll get the gist of how to do this, but initially it might be helpful. Because what you're looking for is you want to see if any of these perfect squares are a factor of the number you're trying to simplify. And is there a factor of 50 that is a perfect square? 25? And 2. Right? 25 times 2 is 50. So 25 is a factor of 50. So I could rewrite this as this, right? And what is the square root of 25? 5. It's the inverse of squaring 5. Undoing that is taking the square root of 5, or 25. So this simplified is 5 squared roots of 2. Okay, so if you put this as an answer as we go forward in this chapter for one of your problems, you're going to lose a quarter of a point for not reducing it or simplifying it to 5 squared roots of 2. Okay, and you're going to start seeing a lot more radicals when we learn quadratic formula and learn how to solve quadratics by completing the square. You're going to start seeing more radicals. So you always have to take that extra time and ask yourself, is there a perfect square that's a factor of the radicand? And if so, you've got to simplify it further. Okay? The last question, if there's a radical in the denominator, you should rationalize the denominator by doing what? Yep. So this is one of those math grammar rules. Didn't know there was grammar in math, did you? Okay. Mathematicians worldwide, if you see a radical in the denominator, this is bad math etiquette. The reason it's bad math etiquette is when I get into fractions and adding radicals, how on earth do I get a common denominator here? When they have different radicands, it's a lot more difficult if you don't have an integer in the denominator. So as you get into more advanced math, this is what you have to do first to keep moving on. So we try and teach it initially with radicals so that you're always in the habit of rationalizing the denominator. To rationalize the denominator, if I look at just the 1 over the square root of 3, I'm going to multiply the denominator and the numerator by the square root of 3. And in doing that, I get rid of the radical in the denominator. It moves to the numerator. So this becomes what? Multiply across the numerator, what do you get? What's 1 times the square root of 3? Square root of 3. What is the square root of 3 times itself? Nope. 3. Remember, I can multiply the radicands when I multiply. So this is the equivalent of the square root of 9. Right? And the square root of 9 is 3. So when rationalizing 1 over the square root of 3, it's actually equivalent to the square root of 3 over 3. If I did the same up here and rationalize this, I get 2 square roots of 5 over 5. Now I can go ahead and get like terms, get a common denominator. They're both integers. It's easier to add these fractions. Okay, this is the purpose of rationalizing. But if you just remember in your mind, you don't want to leave a radical in the denominator. Okay, and that's how you rationalize it here, is you just multiply the numerator and the denominator by the same radical that's in the denominator to get rid of it. Okay, so let's just quickly review a few rules with radicals. I can add radicals if the radicand is the same. Think of this as a variable, like x. If this is x and this is x, I can add them. They're like terms. If this is the square root of 5 and this is the square root of 7, it's like adding an x and a y. I can't combine those. They aren't like. Okay? So if they are like radicands, I can add them. I have 2x and 4x gives me 6x, or 6 square roots of 5. Okay, again, the question that we had on the textbook check, if they are different radicands, and I did 4, I think. I don't know if it was 5 or 6, but I cannot just add these and make it the square root of 9. Can't do that. It's not equivalent. This is not. They have to be like radicands. Okay? But if I were going to multiply these two together, I can do that. This becomes 6 square roots of 20 if I don't simplify the square root of 4 first. And now we look at the square root of 20. Is there a perfect square that goes into 20? 4. So this simplifies to 2 square roots of 5. So this actually would become 12 square roots of 5. When I multiply 6 times 2, I get 12, and then I have a square root of 5 left. We do it down here. Is 12 square roots of 5. How would you simplify the square root of 48? Yeah, 6 and 8 goes in, but is 6 or 8 either one a perfect square?
12 and 4.
Is 12 and 4? Okay, we could do 12 and 4. So you're saying the square root of 4 times the square root of 12. This is 2 times the square root of 12. Is there a perfect square that goes into 12? Yep, so I can do 4 again. 2 times the square root of 4 times the square root of 3, right? And the square root of 4 is 2. So this simplifies to 4 square roots of 3. I could have done it with a faster way if I recognized that 16 goes into 48 evenly. 16 is a perfect square. So if you can find the biggest perfect square that's a factor, you'll save yourself some time. You can still do it this way, but then you've got to simplify 12 again. Okay? So it's just starting to recognize factors that are perfect squares that go into these radicands and being able to simplify that way. Okay? So see how many problems you can get done in web work so I can help.